Okay, so we have this intuitive idea of what a limit is, the idea of what the function is approaching as the x's get closer and closer to a particular target. Now, the question is, how can you pin that down? Well, actually, mathematicians can pin down the definition of a limit quite exactly, using the idea of distance and so forth. For the purpose of calculus and the kind of stuff we're going to do together, it's not at all relevant. But just so you can see that, in fact, there really is an honest-to-goodness mathematical precise definition of a limit, it's sort of fun to see. So what is the actual definition of a limit? Well, let's inspire everything, again, with a picture. So remember these pictures we were looking at sort of have a function, so some sort of crazy function. Maybe, in fact, I'll put a little hole in it just to make things exciting. Are you excited by that? Y equals f of x. So there's the function. And what I want to do is I want to take a look at this particular point right here. So that's the point. Let me call it C. And you see, now we know just by taking the limit, by thinking about what's going on if you're moving along heading towards C, what's the function heading towards? Well, the function, my pens are coming together, and they seem to want to hit right at this height. So in fact, that height is going to be our guess for the limit. So in fact, the limit we're going to guess is that value right there, because that's where my fingers are coming together and want to touch. OK, now, what does it mean for that to be the limit from a mathematical point of view? Well, all I'm going to do is actually capture this spirit. And the spirit is the following. Points that are really, 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 really close to L actually can be found by points that are really, really close to C. So the idea is, mathematically, let's pick a really tiny number, and I'm going to call it epsilon. Usually in math we use epsilon to denote a little teeny tiny number. So think of epsilon as really, really tiny. If you're thinking about epsilon being like a half, you're not even close. Think of it to be like 1 over a billion. Now you're talking epsilon. It's got to be positive, but I want it to be really, really tiny. Now, what I want you to do is I want you to imagine an interval around L that is of basically radius epsilon. So what I mean is go out epsilon up and epsilon down. So that would be sort of like this. So this would be L plus epsilon, and this would be L minus epsilon. And what I want to do here is show or say that, in fact, there must be points that are very, very close to C so that when you look at where the function maps them to, they all live within this tiny band. And so let epsilon be greater than 0. Then, for this limit to exist, there exists some little offset that I'm going to put around C. So we call this usually a lowercase delta. So there exists a positive delta so that points that are within delta, so let me just put in here, this is C minus delta, and this would be C plus delta. So points that are within delta of C, they're all going to get mapped inside of this very, very, very tiny little region surrounding L. So let me say this now in equations. The way I'd say this in equations is so that for all x satisfying the following, the distance between x and C is really close. It's less than delta, and it's positive, so I don't actually look at the value x equals C. Remember, when we take a limit, we don't care what happens at that point, only around it. So I don't want actually x to equal C. And this is just measuring the distance. So this is a fancy way of saying, look at all the points in between here and here, but don't look at C. Don't look at C. Then for every single x satisfying that, we have that f of x is going to be really close to L. The distance between f of x and L will be less than epsilon. And if this actually goes on for every single epsilon, so if for all any possibly small value of epsilon you can think of, this is satisfied, then what we say is, then we say the limit as x approaches C of f of x exists and, in fact, equals L. This is the actual definition. But for thinking purposes, here's the idea. The idea is you can get as close to L as you want if whenever you get as close as you want, no matter how close it is, even if it's really close, if you can always find a little teeny band around C so that all the points around C actually go inside there, well, then what does that mean? It means as you shrink the possible bands here, you're shrinking bands here, but they all go there. That means that these points must be heading toward a height of L. And that's what it means for the limit to exist. It involves picking any arbitrary epsilon and finding an appropriate delta for each choice of epsilon, which, if x is within delta of c, then f of x is within epsilon of L. That's the technical definition, which we'll move on from. Anyway, congratulations and have fun with these limits. I'll see you soon.